Hello and welcome to E233. I'm your instructor, Gregory Myers. In this video, we're going to take a look at another function that allows for us to do memory management. In this case, it's going to be our reallocate function, which allows for us to reallocate the amount of memory associated with an array, for instance, and we're going to focus once again on integer arrays. This video is part of a larger series of videos focusing on our pointers demo, and it assumes that you've watched the first two videos on the malloc function, specifically malloc_01 and _02, as well as potentially the stack versus heap, and that additional video on malloc_01. Now, what I'd like to do is first note that I've provided you with a link to some background information. It's the Wikipedia, or rather Wikibooks site associated with the reallocate function. And specifically what you'll notice here about it is that it returns a void pointer that can be cast to an integer pointer, for instance, or a pointer to a specific data type, but it also accepts a pointer. And so the idea here is that we will be able to utilize the existing data in an array, rather, for example, and then we also can increase the size of it. And you'll notice that just like with malloc, if the resize operation fails, then reallocate will return null, and it leaves the old memory region intact. So we are once again still going to have to leverage two variables for our pointer, but you'll see that isn't going to be the work associated with our malloc_02. So the whole idea here with reallocate is that it resizes a block created by malloc. So let's go ahead and get started here. We're going to set this up fairly similar to our malloc_02. So go ahead and start by copying your function signature over, add it to the list of functions, and go ahead and copy over the start of our function. You'll note that we are reutilizing our display int array. The idea is that it's just going to be a tool then to be able to display all of the elements in our array. And we also want to go ahead and update our switch structure. In this case, I'm just going to borrow from the malloc_02. I'm just going to change it then to reallocate_01. And we should probably go ahead and quickly update our help. Once again, encourage you to go back and to improve on this as you get time. Okay, so at this point, let's go ahead and build it. We can go ahead and close out our snips file, and then let's get started on the code. So we'll go ahead and navigate to the declaration definition. And just like before, we want to go ahead and leverage some temporary or administration variables, if you would, not the least of which is going to be a results variable that is just simply going to control our return value. In this case, we want to be optimistic, and we want to say that our results will be successful, and we simply want to return results. Now, we're going to also need some other temporary variables, or rather administrative variables, because we want to also keep track of the total number of elements in our array to be able to determine when, in fact, we do need to resize it. So to begin with, we're going to go ahead and start off with an nmax like we did in our earlier example. We also want to keep track of the index of the last filled location, which means that we probably also are going to want to have some way to loop through the array. So we might as well go ahead and get an index variable. We want to go ahead and have a temporary variable to do a little bit of management validation, so our value variable, and we want to go ahead and have a flag variable that then controls when we will in fact be done, because in this example, we're going to once again allow the user to grow the array as much as they would like. In other words, to continue putting in data. And we want to have them the ability then to gracefully exit out of our application. So at this point, the only variables that are missing then are the pointers to the actual array. And so once again, what we're going to do is we're going to utilize a current and a new. Now, as in the earlier video, in addition to initializing our results, we want to go ahead and take a second to initialize some of our other variables, my n max, for instance, my index filled, my value we can optionally set to 0, but our done flag we definitely want to set to 0, because that's going to control when the user is done with our application. And then we also want to go ahead and initialize our current to null. And specifically what we want to do is we want to cast that to an int pointer, because remember that once we declare a variable, essentially the value that's at that location is garbage for us. So we want to remember that we want to go ahead and initialize all of our variables, including our pointer variables. So we'll go ahead and initialize both our current and our new to null. And at this point, then what we can do is we can start thinking about the logic of how we want to collect information from the user. And so just like before, what we want to do is we want to utilize our nmax inside of a while loop. And while that nmax is not just equal to 0, but is less than or equal to 0, then we want to continue to prompt the user to enter in, please enter a positive integer value for the initial array size. At this point, we simply want to capture it using a scanf and our %d, and we want to store it at the address of nmax. Once again, notice how this nice simple approach here, this nice clean approach, will simply reprompt the user should they happen to enter in a value that we did not want them to, in this case, negative value. Assuming then that they successfully enter in a positive integer value, then what we want to do is we want to allocate an initial array size. And this is going to be no different from our earlier example, in that what we'll do here is we'll say current then is going to be equal to malloc, but more importantly, we're going to cast the results of malloc to an integer pointer. And what we want to do now is we want to specify nmax times our size of, in this case, we're still going to be working with our integer data type. So essentially what this does is this returns then a block of memory that is going to, the address of which is going to be cast to an integer pointer and then assigned to the current variable. We also want to check to make sure that this result was in fact successful. So we want to check to make sure that our current is in fact not equal to null. And we do that first by checking to see if it is equal to null. If it is equal to null, then we want to print out an error. This says failed to allocate enough memory. And at this point, then we simply want to change our results to exit failure. But under the else branch, we want to do something. Well, what does that do something look like? Well, the idea here is we want to start by capturing information from the user to store in our newly allocated array. Keep in mind that malloc does not do anything about initializing. It just simply carves out a block of memory, gives you the address, So essentially the values in that array are going to be garbage or unpredictable, or however you want to go about looking at this. Now, the other challenge is the fact that we want to continue to grow this array. So the user, every time they enter a new value, if necessary, the array will simply grow without their knowledge beyond their initial array size. So we have to have some gentle way then of them exiting our application. This is where our done flag comes into play. And so what we want to do is we want to set up a while loop that simply says while done is equal to false. We want to collect info from the user. Well, we want to be a little bit specific about what type of information we would like to collect from the user, and that we'd like for them to only provide us positive values. And we also want to give them a way to gracefully exit out of the application by entering in some value, a special value, if you would, that allows for them to exit out of our while loop. And to do that, we'll simply provide them with a print statement that says, please enter a positive integer or -1 to exit. And what we'd like to do is we'd actually like for them to be able to keep track of where they are in the array. So please enter a positive integer for index equal to %d. And what we're going to do here is we're going to simply use or leverage our index filled variable. And we, once again, since we're dealing with integers, are going to collect that using a scanf and the %d, storing that at the address of value. The reason we want to use a value variable here is because it allows for us to do some basic error checking, some basic validation. So in this case, what we want to do is we want to check to see if the value is in fact equal to -1. In other words, the user is done. So the first thing we can do is set done equal to true. It's essentially they're finished using our application. They want to move on. And at this point, then we want to set the flag equal to true or 1 and provide a nice message back to the user saying something like, thank you for using our realloc demo. Now, we have another condition that we wish to check because we were specific that we only wanted positive integers. At this point, we can go ahead and check to see if the user, for instance, entered in a value that was less than -1 or that the value was equal to 0. Either way, we don't want to accept the value. And so what we want to do here is essentially do nothing. And by doing nothing, essentially, the user will come back around through the while loop because the done is still equal to 0 or equal to false, and then will essentially be reprompted to enter a positive integer for the exact same index. So essentially doing nothing means that they are going to be reprompted. And then under the else, we want to store that particular value. So store the value. Well, storing the value is fairly straightforward when you have enough room in your array. But we have to first check to see that we have enough room in our array. And to do that, we simply check to see if our filled index our index filled is less than our end max. In other words, this simply means we have room. Under the else, this means that we have to reallocate or allocate more space. Well, let's focus on the allocation of more space and see what this means. We'll come back to the part that we have enough room in just a minute. So in order to allocate more space, if you recall, we can use our realloc function. And what we want to do is we want to pass to it the address of our existing array, or the existing location in memory of the start of our array, and in hopes that we have enough memory so that we can reallocate it and get another pointer to another block of memory. So let's see how this would work. And this is where our new pointer will come into play. So we say new then is equal to realloc, and we want to pass to realloc the address stored in the current one, and then we want to choose a larger size, because the idea here is that we want to grow the array. We'll have a discussion in just a minute by how much, but to accomplish this, we're just simply going to leverage our nmax plus 1 times the size of an integer. I think I might have been a little bit carried away with my parentheses here. Technically, you get away with one less, but hopefully you can see here that essentially what I'm going to do is I'm going to multiply these two values together to be able to get the new size of the array. At this point, we want to go ahead and check to see if new is equal to null. If new is equal to null, we have a problem. And we want to notify the user. So printf error failed to allocate enough memory. We want to make sure that our results now reflect that. In this case, that they reflect failure. And more importantly, we want to stop trying. So in this case, what we want to do is we want to say that done is equal to true, or done is equal to 1, such that the next time around when we hit our while loop, we won't reprompt the user for another input value. Now, what do we do if, in fact, the value, that the memory allocation was, in fact, successful? Well, under the else branch, then, what we want to do is we want to assign the value stored in new to the current variable. Because essentially what this means is the address that was stored in new is now assigned to the current variable. So essentially you can think that the current variable points to this new block of memory. And at this point then, what we want to do is we simply append that new value. So in this case, what we'll do here is we'll say current square brackets index filled is equal to whatever value the user entered. And at this point then, what we want to do is we want to increment our index filled, as well as incrementing our nmax. And so essentially what we're doing here is we are growing it by one integer size. So grow by exactly one integer. All right, so we said we were going to come back to what do we do if we have room. Well, it turns out that essentially if we have room, we don't have a problem. We can simply say current index, or current square brackets index filled is going to be equal to value. And at this point then, the only thing we need to do is we can increment our index filled. Now you'll note here that we could, if we wanted to, get a little bit fancy with our logic because we have a little bit of code reuse here, and that we could essentially, after allocating a new block of memory, we could simply then just insert the value in that new location in the array. Whether or not we had to grow the array wouldn't really matter. In other words, the logic essentially would be similar. The only thing is, though, under the scenario in which we have new equal to null, we would then want to check to see if that was the case, and then only attempt to insert the new value into the array if, in fact, the reallocation was successful. So if it seems like there's a little bit of code duplication here, it just makes our logic perhaps a little cleaner and a little straightforward, a little more straightforward. So at this point, what I'd like to do to help us understand how this works, I would like to go ahead and insert a couple of printf statements, much like what we did in our earlier example with our malloc _02. As a matter of fact, this would probably be a great opportunity for you to pause the video and to go back to your earlier example and to maybe copy and paste some of the code over. That's exactly what I'm going to go ahead and do here, because I'm going to come up here then to malloc, and you'll see here that we've already spent a little bit of time creating a nice little table here that essentially handles both our current and our new array pointers, integer array pointers, and just once again creates a nice output. We'll modify what the table says in just a second. So the first place we want to put this is after collecting our n max, but before we allocate it. So essentially what we're going to do here is we're going to initialize them to null, but before we've actually allocated current. So if you recall from earlier that our display int array has logic in there to check to see if it is equal to null. And if it is equal to null, then essentially do nothing about it. In other words, don't attempt to print out an element, any elements. So what we want to do now is we want to check to see what this looks like after a successful initial allocation of memory using malloc. So essentially inside of our else, when we're tasked to do something, at this point then, this is going to be after the initial allocation of memory. And at this point, then what we can do is inside of our while loop, particularly at the end of our while loop, so we'll be very careful here to make sure that we get it at the end of our while loop, we can once again print out a nice table showing the addresses stored not only in current, but also in new. And so here will be after each iteration of the while loop. And then specifically what we want to do is we want to look to see what happens after we make a call to reallocate. And what we're interested in seeing is what is the contents of the current and the new variables, both before and after reassigning them. So you'll see here, essentially, this is the critical assignment here. We want to see and understand exactly how this works. So what I'm going to do is I'm going to carefully put a table both before and after but notice here how I'm intentionally putting it before the n max. I don't want to disturb this value, at least not without doing it consciously. And so what we want to do here is put a little bit of notes in here. So this is going to be after realloc, but before assignment. And then this is going to be after assignment. In other words, that now our current should point to new. Now, let's think about this for just a second. Before the assignment, but after the realloc, our new array should technically be one element larger than the current array, or at least the block of memory. So in this case, what we're going to do is we're going to ask that our display int array print out one additional value. We expect there to be garbage there because we've not yet assigned the value. And then in this little printf block right here, what we want to do is we want to add one more, not only to the current array, but then we want to see what does the new array see, or what does the new array pointer see? Because remember that we are essentially assigning the address of new to current, and then we turn around and we update our current array, because remember though that current is really just a pointer to a block of memory, and essentially we're updating a value in that block of memory. So what should happen is that this call to display int array should magically see that new value, even though the new variable didn't change. Nothing changed about it. The address stored in this variable and the address stored in this variable should be the same. So let's go ahead and build it real quick. Let's see if we've got any typos. All right, good, we do. Let's see what we've got. Ah, missing semicolon. That's not too bad. That's definitely expected when we've written so much code. Let's come over to our console. We'll go ahead and clear our screen real quick. And in this case, what we're going to do is we're going to first check to see that our help has in fact been updated. Looks promising. And what we want to do is we want to run our realloc 01. Much like in our malloc 02, we're first going to be prompted for the initial array size. We're going to start off 3. No surprise there that current and both think that there is nothing because they're both assigned value of null. After the initial allocation, you'll see that there's garbage for all 3 of my array locations, but you'll see the addresses. We'll try to focus on this a little bit here. So it's 0CB0, 0CB4, 0CB8. And then we'll put in some values here. I have a 123. You'll see that I'm successfully assigning that first value. Nothing's happened though to my new array. Okay, so even after each iteration of the loop, nothing's really happened here. Likewise, my second value, I'm simply updating the second location in memory. No changes in memory right now. No changes in the memory address. 345. Now you'll notice that I have all 3 of the elements are filled or updated. Still no change to my new, but now this is where it's going to get interesting. So I'm going to put in 456, and you'll notice here that I have, after my realloc, but before my assignment, my current still thinks there's 3 values in there. My new, of course, knows better because it's been reallocated. It's got an additional chunk of memory now at its disposal, and you'll see that it's in sequence. And now after the assignment, so essentially when I assigned the address that was returned by malloc, that was stored in new once I assign it to current, now essentially current and new point to the same location in memory. They both have the same value now stored out here at the end. And you'll notice here that I have the same thing after each iteration of the loop. So hopefully now you can see that we've grown one block of memory, unlike in the earlier example with malloc where we had to grow 2 separate blocks of memory. Realloc will allow for us to grow 1 block of memory. If it's possible, you will keep the same initial address. However, that's not guaranteed. So as a matter of fact, let's keep going. Let's see if we can trigger this. It might take many more iterations of this because you'll see still my root value is 0CB0. This would It's probably going to be an example of something that we would want to do in some sort of automated fashion. Yes, because as you can see, I'm not really changing my initial address of my array. We'll get plenty of opportunity to see this in the future. Basically, if it can't allocate a continuous block of memory, then what it will do is it will give you a new root node, or rather a new root address. And at this point, then we could continue on testing this, or we can simply just type in -1 to exit, and you'll see that we get a nice prompt back that says, thank you for using our realloc demo, as well as just printing out our table one more time. So hopefully you have found this video useful. As always, if you have any questions or comments, don't hesitate to email me, and thank you for watching.